Assalamu alaikum. Welcome again. In most of the problems, we take K as a constant value. Thermal conductivity is constant. But in reality, it's a function of time, okay? Not that much sensitive to temperature. I'm sorry, not function of time, it's function of temperature. And not that much sensitive to temperature, but when you have huge temperature difference between 2 points of the same material, so that means the conductivity will change depending on the temperature. So you should consider that function not as a constant, okay? But if you see that beta is low coefficient, okay, low coefficient. So when let's see, when temperature is not too much high, okay, temperature is like relatively low, okay, you get K 1 plus beta T squared term, where 1 is too much bigger than beta T squared, where you can neglect that beta T squared and say 1 plus beta T squared is equal to just 1, or approximately equal to 1. So you will get K is K0 times 1 plus 0 approximately, right? So you will have K is equal to K naught. So here you can treat at this regime, you can say that that is constant. But sometimes if, let's say, 1 and beta T squared, when you compare them, it's not that much low, okay? T is not that much low. And we cannot neglect it, so we should take K as a function of temperature, okay? So let's see how do we apply this to get heat transfer coefficient, okay? So you have minus K dt over dx, okay? So we want to find, like we want to integrate K with respect to temperature to get like expression of Q as a function of temperature, okay? So let's see how do we do that. So we have minus K sub 0 plus, I'm sorry, minus K sub 0 multiplied by 1. Let's distribute it. So K sub 0 over K sub 0 beta T squared. So you will have temperature squared, then dt over dx is equal to Q, okay? So we can integrate dt here, and dx we send it to other side, so q dx will be equal to integration of this part as a function of the temperature. So you get like from 0 to x, and here from t naught to tx as a function of x, okay? So you will get, so since from 0 to x and q is constant here, constant heat flux during this okay wall, we can say solid wall, we have constant heat flux. So you will have q go out and you have 0x, you get, that will give you x only. So qx is equal to so this will be minus k naught tx minus t naught when you integrate it, and you have minus k naught beta, then t naught, I'm sorry, tx power 3 minus t naught power 3. And you have over 3 from the integration. We increase this and divide it by 3. So here how we express Q as a function of temperature, and you can say also Q for a specific x value will be equal to minus k naught x t x minus t naught. T naught is just the wall temperature, okay, minus when x equal to 0. Here you have also 3x, or let's make it like this. So that's how we know heat flux like if you remember, if it's constant, we get just Q is minus K delta T over L. It's easy, right? But if you have like varying thermal conductivity with respect to temperature, you should consider all these and calculate the heat flux based on these values. Thank you for watching.